Good morning, everyone. Today we are starting a new topic called magnetism. And this week we will be looking at magnetic field and also the induced magnetic forces. We will be looking at charges that are moving in the existence of a magnetic field and electric field as well, both. We will be looking at wires that are carrying currents in the existence of magnetic field, also the torque and the potential energy on magnetic dipole and magnetic dipole moment. Okay, so let's start with the definition of the magnet. What is the magnet? The magnet is a material that produces magnetic field. So a permanent magnet basically stays magnetized for a long time without external aid. Those magnets, they do have two poles. One of them is north and the second one is south. And they always point, the north is pointing to the North Pole and the south magnet is pointing to the south pole of the Earth. Now, magnets, they do pick some objects, not many. They do pick paper clips. They won't pick up plastic, glass, or some other material, metal material like copper, for example. So, unlike electric charges, which have the positive and negative poles, they appear to be monopoles, such that the electric field will be going from the positive charge toward the negative charge. Magnets, they do exist in pairs, such that they always have the magnetic field as closed loop, and magnets are in pairs or dipoles. Unlike poles attract, similar or like poles repel. As you can see, if you bring two magnets trying to bring the north closer to each other, they will repel each other. The opposite is when you bring the north toward the south, you will see that there will be an attractive force between them. So magnets do not exist in monopole as charges, like the positive charges and negative charges. Magnets do exist in dipoles. So materials that are attracted to the magnets are called magnetic material. All electrically neutral objects can be attracted to a charged object. It's different in magnets. So the magnets have magnetic fields, as we said. Those magnetic fields, they do exist such that they create always a closed loop, different than the electric field. So if we look at the magnet, basically the magnetic field lines will go from the north toward the south, and if you put compasses around this magnet, you will see that those little magnets, they always have the north pointing toward the south, such that they overlap with the magnetic field. So it is always tangential on the magnetic field, as we will see in the next slide. How does the magnetic field look like? So this is the magnetic, those are the magnetic field from the north going to the south, and then inside the magnet they continue the loop such that they become closed, right? So they always go from the north toward the south, and then they close the loop within the magnet itself. If we put an iron fillings, as you can see here, they tend to take the shape of the magnetic field lines, as you can see, such that they those ones, they always point from the north toward the south. So as we said, they close through the magnet, such that they go from the north, coming back to the south, and they close within the magnet. Those magnetic fields, at any point, the tangential component defines the direction of the magnetic field. So take the tangential component, then this will be the direction of the magnetic field as we see here, right? And they tend to close, as I said, to close the loop within the magnet itself. They always point toward the south. They leave from the north, pointing from the north toward the south. If you take the magnetic field at this point, you'll see that the magnetic field is direction is this. They are concentrated closer to the pole, which basically represents the strength of the magnetic field, and they don't cross. So this is the magnet inside the earth. If you look at, if you have any compass here, you will notice that your compass, the north, will be pointing up, and the south would be at the bottom, such that they are in line with the earth magnetic field. However, as you can see, in order for my magnet that has the north and the south, north pointing to what I know, the North Pole, I have the south magnet right there at the North Pole, and that's why they always tend to point to the north, and the south would be pointing to the south. So the magnet of the earth is, as you can see, is opposite than what we have our magnets pointing to. Now let's look at this example here. In this example, we have two identical bar magnets that are placed rigidly and anti-parallel to each other, as shown. At what locations, if any, is the net magnetic field close to zero? So we've seen in our example that the magnetic field is going from the north, right? Going from the north toward the south. So I can think of this point where I have the magnetic field going this way, and also from the north, since they are identical, the magnetic field would be pointing this way, which means right at this point here in the middle, which is the C, I have two magnetic fields that are equal and opposite in direction. So this is the point that I'm anticipating the magnetic field to be closer to zero. So the magnetic field for the magnet that does exist in dipole representation is very similar to the electric dipole. The field goes from the positive toward the negative. Here, the field goes from the north toward the south. The only difference is those are monopoles, the negative and the positive charges. However, the magnetic field have to close the loop, and they close the loop within the magnet. So they have no start or end, different than the electric dipole that they have a start point and ending point. There is no monopole in magnetic field. Then you cannot separate the north from the south. Now, if you try to physically cut a magnetic bar into two pieces, you will be generating two new dipoles of magnet, such that the only difference is the size, which basically is going to result into less strength magnets, but at the end they will be the same. They will have north and south. So, what is the symbol for magnetic field? Magnetic field is given the symbol B. B vector. It is a field. It's a vector field. So the symbol here is B with the vector. Remember the electric field was E.